Another day mastering
linear algebra.
What did we learn yesterday? I think yesterday we went over ordered sets, how to do proofs, and then we got into complex numbers. So ordered sets are not the same as regular sets. They are sets in which the order of the elements does matter, whereas normal sets, the order does not matter. The order of the elements doesn't matter, okay? How to do proofs. So the first thing you want, there's like 4 steps. First is you want to write out your hypothesis, what you're trying to, what you're given, and then the conclusion, what you're trying to prove in complete sentences. Second, you're going to want to decide which way you're going to try to prove the prove it. How do we do that? Well, you can do it by directly, you can do it by via contrapositive, or you can do it by reductio ad absurdum. How do you structure these 3 is different. This is basically if H then C. This is if not C then not H, and then this is if H and not C then C. So you can rewrite your hypothesis and conclusion in these 3 different ways, and then kind of go off intuition, which one you think is going to be the best approach. Step 3 is you gather previous theorems and proofs that may be of use to you in this proof, and then finally, it's basically just intuition, perseverance, guess and check, essentially. Okay, complex numbers. Complex numbers is a massive set of numbers. I think it may be all the numbers, but maybe not. Complex numbers is basically any number that can be written in the form of a plus bi or a plus ib, where I is an imaginary number. I equals the negative of square root of 1. No, the square root of -1, I mean. And even if a and b are 0, you still have a complex number. We'll get that in a second. The way you algebraically and arithmetically manipulate complex numbers is the same as you would normal regular numbers, treating I as a variable, with the only exception being that I squared equals -1. Cool. What else we got? Right. If A equals 0 and you have something for the value of B, then that's called a pure imaginary number. If you have no B value, saying B equals 0, so no imaginary part of the complex number, then that's called a real number. So real numbers are a subset of complex numbers. That's why it's like, dang, complex numbers are enormous. And so our pure imaginary numbers are also a subset of complex numbers. Okay, what else we got? Cool. Yep. Okay. So imaginary numbers can also be written, or complex numbers, I mean, can sometimes be denoted by a single variable or letter. And the real part of the imaginary number, or the real part of the complex number, can be denoted as RE parentheses, with the letter denoting the complex number within the parentheses. Same thing with the imaginary part of the complex number, can be denoted as IM parenthesis with the letter of denoting the complex number within it. Cool. Okay, so complex numbers are only equivalent when both imaginary and real parts of both equations are equal. So the imaginary and real number parts of this complex number have to be the exact same as the real has to be the same as the real, and the imaginary has to be the same as the imaginary. Okay. Pure imaginary numbers, real are a subset of complex numbers, and pure imaginary numbers are a subset of complex numbers. Cool. Right, and the set that contains complex numbers is denoted as capital C. It's called a complex number system, I believe. And that's it. That's where we're at. So now we're getting into the complex plane today. I'll be back in a second. I have no idea really what the complex plane is, but I guess I can see from the images and make sense of it pretty quickly, but I'll be back in a sec. All right, guys. Just went ahead and read about the complex plane. Simply, the complex plane is basically just graphing these complex numbers in a coordinate plane. So the complex number a plus bi, that form, you would basically say the real part a, comma, the imaginary part b, parentheses. So that's the point. It can be also written as a vector or drawn as a vector on the coordinate plane. A, B, A, B, A, B, A, B, A, B, X, Y. Yeah, it's like X, Y. So the x-axis is called the real axis. This is where the real number part of the complex number is plotted, and then this y-axis is called the imaginary axis. It's where the imaginary part is plotted. Okay, then we talked about complex conjugates, also known as just conjugates. Very simply, you just reverse the sign of the imaginary part. So instead of a plus bi, the complex conjugate would be a minus bi of that specific complex number. You denote it with a bar over the symbol that's denoting the complex number. So if this complex number is denoted z, then the complex conjugate of z is z bar. Yeah. Cool. So that's okay. One other thing is they're saying the complex number system C is similar to R squared, except for a multiplication. You can't multiply two vectors in the R squared to get another vector. You get a scalar. But considering we haven't studied R squared yet, we're just going to leave it at that and keep moving forward. All right. I'm now going to read some more about complex conjugates. And then I'll be back in a second. All right, so I just read more about conjugates, as well as modulus, aka absolute value of a complex number. Okay, so if z, or if a number is a complex number, then z bar is equal to z, meaning the complex number is equal to its complex conjugate if and only if the number is a real number. Okay, what else do we talk about or read about? So the modulus, right? So, okay. A complex number multiplied by its complex conjugate will give you a non-positive or a non-negative real number. And this is denoted as the absolute value of z. So the absolute value is z in between the absolute value bars, aka the modulus. And the modulus is the same thing as the length of the vector that corresponds with the complex number within the complex plane. I think that's everything. Cool. It's moving. We're moving. Yeah, well, how do we move so fast through this? This moves faster than the Make It Stick book, and that's a little general purpose book or general audience book. This is a textbook. I don't know. Maybe there's actually less words per page on these pages, just because there's lots of spaces and whatever. Now we're going to read about reciprocals and division of complex numbers. Oh. All right, I'll be back in a sec. All right, so the reciprocal is also known as the multiplicative inverse, and it's basically if z is not equal to 0, then the reciprocal of z is 1 over z, aka z to the power of -1. And so using the idea that the z times z bar equals the absolute value of z squared, we can plug that in into this equation where The reciprocal, the definition of the reciprocal is z times 1 over z is 1. We take that, and then we can apply a formula, or the definition of the complex conjugate or something like that. Anyway, we're getting into formulas now, so I think I'll digest this formula a little bit more tomorrow, these two formulas that are, yeah, because that was the timer. So that's what I'll do tomorrow, is I'll start working on that, those formulas, and understanding what they're getting at with these formulas for, yeah, I'll talk to you guys tomorrow. See ya.